Hi, I'm Olivia, everyone's favorite math teacher, and in this video we're going to look at another one of the results from the mean value theorem. Specifically, we're going to be looking at the first and second derivative tests and what they tell us about functions. So here's our first derivative test, and it is a direct result of the mean value theorem. So we already know that we can find critical points based on picking a point that is on some interval, right? So the way this works is we simply use those critical points as the endpoints of some interval. And then by applying the mean value theorem, we can determine what the behavior of the graph is on that interval. If we know that the graph is increasing or decreasing, then that lets us say basically what's happening there. And then the other thing that we also know from this is that we can definitively say what is going on in a graph at a point. So we kind of already knew this because we know that when we take the derivative at a point, we're finding the slope at that point, right? And we know that the slope tells us not only what a value is, but also kind of what the behavior is, because a slope is directional. We know that it's increasing if it's positive and it's decreasing if it's negative. But the mean value theorem lets us say that with just a single point, since we're getting the slope at that point, that we know what the behavior should be at that graph should we continue to move forward. Basically, it gives us a rigorous way of using that conclusion instead of just a conceptual way. Now, the thing that this lets us do that's powerful here is it lets us identify maximums and minimums without having to resort to the previous test we used of the closed interval test. And just to remind you, that required us to go back to the original function, which might be a difficult calculation. In this situation, because we can find the behavior of the interval before the maximum or before the critical value and the behavior of the interval after the critical value, we can then just say, well, since we know that at a maximum, you go from increasing to decreasing, that's the definition of a maximum, and we know that at a minimum, you go from decreasing to increasing, the definition of a minimum, we can use the first derivative test and the behavior of the graph to define whether or not our critical point is a maximum, a minimum, or an inflection point. Strictly based on what's happening with the sign changes. So we don't have to actually calculate full-on values. Now, you'll notice that we say near C and not at C, and that's because we're not talking about at that point specifically, because we can have the situation where the derivative does not exist. So we care about right before the derivative and right after the derivative because, that's what's going on here. So in the case of this one, we are increasing. We don't exist because we have a vertical tangent at this point. And then we're increasing again, so we know that this would be an inflection point, right? And then, of course, here we go increasing to decreasing, so this is a maximum, which you can see from the graph. But the whole point is we want to be able to check the function without having to look at the graph. And then the other advantage is that sometimes looking at the intervals, we might accidentally pick an interval that is inappropriate, like we saw way back when we were first looking at limits. Now, we still do have a little bit of a problem here, because the first derivative test is absolutely great for checking at any given point what's the value and what's the behavior. So we know, am I increasing or decreasing at a point? But for checking at the maximums and minimums, we still get this little bit of an issue that we still have to go a step to the left and a step to the right on an interval in order to check it. And we still might run into this problem of what happens if I accidentally step into an interval that's maybe inappropriate. Maybe I've stepped too far on a cycle of a periodic function, for example. Wouldn't it be great if I could look just at that point and only be able to check at just that point in order to be able to test if this was a maximum or minimum without having to look anywhere else? And the good news is we can. That's where the second derivative test comes in. So here's our second derivative test. And the second derivative is the change of our function. Basically, think of it like acceleration. And the idea of concavity is we're talking about the curvature of the graph. Or in other words, we're talking about how and in which direction is our change changing. And conceptually here, we're saying that the way we define concavity is that we have our function and then we have our tangent. And our graph is concave up if the tangents are lifting the graph. So as the tangents go, the function is constantly above them. And then our graph is concave down if our tangents are above the graph. So as the tangents go, the graph is constantly having to be below those tangents. So it curves down. Now, calculation-wise, the way we would look at this is we would take the second derivative. And so if the second derivative is positive, greater than 0 on an interval, then that means the function is concave up. Those tangents are angling upward. And if our second derivative is negative on an interval, then f is concave down on that interval. Those tangents are angling downward. They're pushing our graph down, okay? So that's helpful because, again, that lets us know the shape of our graph, that lets us know the behavior of our function. But the other very specific benefit here is that this lets us identify maximums and minimums without having to step to the left or the right. Basically, without having to find an interval to test on. We can look at exactly a critical value, and then after taking the first derivative, we can take the second derivative to say, is it a maximum or a minimum, by using the inflection. Because remember, if it's a maximum, it's going to be concave down because it's the top of a curve. And if it's a minimum, it's going to be concave up because it's the bottom of a curve. So therefore, if we know we're at an inflection point, so the first derivative is 0, we can take the second derivative, and if the second derivative is negative, we have a maximum because we're concave down. And then if we take the first derivative, we get 0, so we're at a critical point, and the second derivative is positive, so therefore we know we're concave up, we know we're at a minimum. However, if we take the second derivative, we find we're at a critical value. Remember, if it does not exist, we can't take the second derivative, which is why we didn't include it here. So if we take it and it's 0, but we also get 0 for the second derivative, we can't conclude that it's a critical value because we actually could be at one of those weird situations where we could be a maximum or a minimum, but it's a weird one. You'll see one of those in the examples we do later. So the test is inconclusive, and we would simply have to go back and use the first derivative test instead. So this allows us to once again test without having to go back to using the interval method that could potentially lead us astray in specific kinds of functions, okay? Now, the other advantage of the second derivative test is it lets us find the inflection points that the first derivative test doesn't identify. Because here's one of the things. The first derivative test will identify those inflection points where we get either a 0 or it does not exist. So those kind of like extreme inflection points. But we actually can have very gentle inflection points where the curve just kind of gradually changes its shape, and we won't get a 0. We won't get a thing that we get identified on the first derivative. And so when those happen, that's when we get these nice kind of smooth changes between our first derivative and our second derivative, or our maximum and our minimum. And so the way we find those is we take the second derivative, and we'll see that we have a change in inflection at that point. So there's our second derivative test. Let's go ahead and look at a couple of problems and see how we would actually apply these. So when you put it in a table, you can see that it's really not that bad. We basically say that if f is continuous on a closed interval and differentiable on an open interval, then our first derivative test, basically what we look for is where is f greater than 0 or less than 0, and that will tell us when f is increasing or decreasing. Because remember, when f is equal to 0, we are either a maximum, a minimum, or an inflection point, right? Those are what we call our critical values. We learned that with Fermat's theorem, right? And then if f is a critical value, then if our first derivative is going from positive to negative, we're at a maximum. If it's going from negative to positive, we're at a minimum. And if it is not changing sign, then that's when we are at an inflection point. Our second derivative test tells us that when our second derivative is positive, we are concave up, meaning we have a positive acceleration. When our second derivative is negative, we're concave down. We have a negative acceleration. We're trending downward. And then for here, if we're at a critical point, when we take that second derivative, if our second derivative is negative, so less than 0, that means we're at a maximum because we're concave down. If our second derivative is positive, we're at a minimum because we're concave up. And if our second derivative is equal to 0, our test is inconclusive. We might be at an inflection point, but we can't really be sure because we just can't be 100% sure. We would have to go back and check our other tests just to see if it's an inflection point. And then just a reminder here that if f is continuous, we can find those inflection points by looking for those critical values and then just checking it with our first derivative test. So let's go ahead and just see how this gets used and how we can use this to examine a function, and then we'll go on our way. So go ahead and give these 3 a try. We'll do that first one together, but these last 2 I'll show you after the outro. And I'll show you that first one in 3, 2. So how'd you do? Now, I do want to remind you, before we get moving further on this, use your technology. I certainly am. I know that doesn't look like it because I'm using a chalkboard and chalk here, but off screen I absolutely am using my graphing calculator and Desmos, okay? So in order to work on this, I actually started with part B, then I did part A, and then I did part C. And the reason I did that is because in order to find those intervals, you're going to want to know where your critical values are, which means you're going to want to take your first derivative and look for those zeros in order to figure out, okay, where are my possible maximums and minimums using Fermat's theorem, right? And so since you've already taken that first derivative, you might as well then figure out which ones are my maximums and minimums. And then once you know your maximums and minimums, you can then find that interval much easier, okay? Now, I did not use the graphing features to do this. I simply used the actual calculator functions in order to figure out, my actual values here after I used my derivative test. So remember, use your technology, but try to legitimately use the calculus portions that you're being tested on, because when you're taking something like an AP test, there will be non-calculator portions where you'll have to explain how you used the actual tests that you're being asked to use, okay? So here's how we do this. For the B part, we take our first derivative, solve for 0 in order to figure out where I might find my maximum minimums, and then I use my second derivative to figure out which one is a maximum, which one is a minimum, or if either are. In this case, because my -3 got me a negative value, that told me it was a maximum because I'm concave down, and my other one, my 2, was a minimum because it was a positive value, so I was concave up. Then I plugged those back into the original function to get the y values, and that told me where my maximum and minimums were. From that, because this is a polynomial, I knew that up to that maximum, I must have been increasing, and then between the max and the min, I was decreasing, and then again, from the minimum onward, I must have been increasing again. So that's how I got my intervals. And then for the inflection, I went to my second derivative, and we know from the definition that on the second derivative, wherever the second derivative is positive, I'm concave up, and wherever the second derivative is negative, I'm concave down. So because this is a linear function for my second derivative, that means basically I just find 0, and then everywhere after 0, I'm concave up. Everywhere before 0, I'm concave down. So I set up the inequality and said 12x plus 6 is greater than 0. That happens at -1/2. And because it's linear, that means that, okay, well, less than 0 must be before 1/2. So that told me my inflection point was at -1/2, and then 18.5 when I plugged -1/2 back into my original function. So I hope that overview of the first and second derivative test helped you out. And of course, if you have any questions, you can drop into the comments or join us on Discord. And the answers to those last two problems will be after this outro.